Hello friends, welcome back to all about structural analysis and design. So in this video we shall see what is T-beam, and also we shall see how to analyze a T-beam. Analyze in the sense we shall see how to calculate the ultimate moment of resistance with the help of codal provisions. So whatever the section I have drawn here is a section of a T-beam. Okay, we have seen the rectangular beam, how to analyze, and also we have seen the design of singly reinforced beam and analysis of doubly reinforced beam also. Okay, so you know the portion of the beam. Okay, then what is the difference between that beam and this particular T beam? If you see practically the casting of a beam and slab, it is casted at a same time. Okay, the beam is not casted differently and slab is not casted differently with the concrete. Okay, beam and slab is casted simultaneously, and this gives rise to a T beam or a T section. So whatever the upper part you are seeing, this rectangular section is a slab section, and whatever the bottom part of this particular section which you are seeing is known as the beam section. So this combination of slab and beam gives rise to a T section, which is also known as T beam. Okay, understood? Because we don't cast differently or separately the slab and beam, which is practically impossible. Therefore we cast this slab and beam at the same time, and this gives a section, a T section or a T beam. So therefore this upper part is known as, or the upper part is slab section, and this is a beam section, and together we call it as a T beam or T section. So what are the parts of this T beam? So whatever this horizontal distance of this slab section, whichever or whatever you are seeing, is known as the width of flange. Remember, the T beam is also known as flanged beam or flanged section. Okay, so this is the width of flange, then the depth of flange, width of web. Okay, so this is known as flange and this is known as web. So these are the notations you have to remember. So this is denoted as a BF. Okay, so this is known as BW. B is for width and this W is for web, width of web and width of flange, and this is DF, depth of flange. Okay, and again the effective depth is there. Okay, whenever when we go for this analysis, I shall show you the effective depth also. Now what we shall do, we shall analyze this T beam, or we shall find out the moment of resistance for this particular T section. So the data given is, or you can write down the question like this: find the ultimate moment of resistance, ultimate moment of resistance of a T beam having BF as 750 mm, then effective depth D as 400 mm, then width of web, that is BW, 250 mm, then depth of flange DF as 100 mm, then EST they have given 5 bars of 20 mm phi, then again steel FY they have given as 415, and FCK 20, both are Newton per mm square. Okay, so this is the data they have given for a T section to find out the ultimate moment of resistance. Okay, so this BF is 750 mm here. Okay, like this you can mention 750 mm, the effective depth, and these 5 bars, 520 mm bars are placed in the web. 1, 2, 3, 4 and 5. Okay, so these are 5 bars of 20 mm phi, and the effective depth, that is from this point to this point, it is D, which is 400 mm, and width of web is 250 mm. Depth of flange is 100. So all the parameters are given, and the steel used is Fe 415 Newton per mm square, and the grade of concrete FCK is 20 Newton per mm square. So all the parameters are given. So the first step will be to find out the area of steel. In terms of bars they have given, we have to find out the area now. Now AST equals to 5 into pi by 4 d square. Okay, this is diameter d, don't get confused with the effective depth. Okay, so 5 into pi by 4 into 20 square. So the AST comes out as 1570.8 mm square. So now you have calculated the area of steel. Then what you have to do, listen carefully, that neutral axis, there will be two cases. The neutral axis lies inside the flange and the neutral axis lies outside the flange. Outside the flange means it lies in the web here, somewhere here, and inside the flange means somewhere in the slab section it lies. So whenever you start a problem or analysis problem of a T section, always start by assuming the neutral axis lies in the flange. Always you have to remember that. Okay, so assume the neutral axis to lie inside the flange. So same thing I will mention here, assuming neutral axis to lie inside the flange. Okay, then what happens, you have to go to page number 96. This is your annexure G, and you have to go to page number 96 and separate. They have given flanged section here. If you can see here, G2 flanged section. Okay, we will see here G2, but before that, when you assume the neutral axis to lie inside the flange, then what happens, then you have to directly use this formula, the first formula, that is XU by D equal to 0.87 Fy AST divided by 0.36 FCK B and D. But the only thing you have to remember is, in place of B you have to substitute BF. Okay, and you have to find out the neutral axis value. Okay, neutral axis value you can find out by substituting in this particular equation everything. Then if it lies outside, then we'll see what happens. First you have to assume that it should lie inside the flange. So from page number 96, same formula you have to use, that is XU by D 0.87 Fy AST divided by 0.36 FCK BFD. Only in place of simple B you have to replace it by BF, because you are finding out the neutral axis which is lies inside the flange, and the breadth of flanges you have to substitute. Then just substitute these things. 0.87 into Fy is 415 and AST you have calculated 1570.8 divided by 0.36 FCK is 20, BF is 750 and the effective depth is 400. So this XU by D value comes out to be 0.2625. 0.2625. So this is the value of XU by D. XU by D 0.2625. You know the D value, effective depth value, so transfer it to that side. 0.2625 into 400. So XU comes out to be 105 mm. Now you got the neutral axis, the location of neutral axis. But df equal to 100 mm. The depth of the flange was 100 mm. So what it means, our assumption is wrong. Therefore, our assumption is wrong, because neutral axis lies outside the flange. Correct? This XU is 105 and our flange depth is 100 mm. So it crosses the depth of flange. Therefore, the neutral axis lies outside the flange. Okay. Then what you have to do, because the neutral axis lies outside the flange, therefore let us obtain the new value of XU. Correct? This XU was the assumption that the neutral axis lies inside the flange, and then we have calculated that XU, but it was found that the neutral axis lies outside the flange, because XU value was 105 mm and our DF value is 100 mm. So 105 is greater than 100, therefore the assumption is wrong and the neutral axis lies outside the flange. Now what you have to do, let us obtain the new value of XU, because this assumption was wrong. That's why again we have to calculate once more the value of XU. How? By equating total compressive force to the total tensile force. Okay, so what you have to do, total compressive force, that is Cu, should be equated to total tensile force, that is Tu. Cu should be equal to Tu. Now total tensile force is given as 0.87 Fy AST. So when you get back to the stress block parameters, if you see any standard textbook, the derivation of these formulas are given. So the total tensile force Tu equal to 0.87 Fy AST. Just substitute here 0.87 into 415 into 1570.8. So it comes out to be, Tu comes out to be 567137 newtons. So this is your total tensile force. Now you have to calculate total compressive force. Total compressive force, that is Cu. So Cu is given as 0.36 FCK XU BW plus 0.45 FCK BF minus BW into YF. YF is nothing but equivalent stress block parameter. We shall see how to calculate that YF also with the help of codal provisions. Now we shall get back to this page number 97 of IS 456. In page number 97, everything they have mentioned, where YF equal to 0.15 XU plus 0.65 DF, and XU we have to calculate. Okay, so first you can just calculate YF in terms of XU, then you can just substitute in the Cu formula, and you can equate it to total tensile force. So I hope this is clear. This from stress block parameters, what you can say, from derivation, these things I have taken. So total tensile force 0.87 Fy AST, total compressive force 0.36 FCK XU BW plus 0.45 FCK BF minus BW into YF, where YF is equivalent stress block parameter. So this YF will calculate first from page number 97. From page number 97, IS 456 2000, YF equals to 0.15 XU plus 0.65 DF. So here DF is known and XU we are going to calculate. So just substitute DF and get YF in terms of XU. So YF will be 0.15 XU plus 0.65 into 100. So YF will be 0.15 XU plus 65. So substitute in CU. So when you substitute in CU, the equation looks like this. So CU equals to 0.36 into 20 into XU is unknown into 250 plus 0.45 into 20, 750, that is BF, minus BW, that is 250 into YF. YF is 0.15 XU plus 65. Then just simplify this. CU equals to 1800 XU. When you multiply these things, you will be getting 1800 XU plus this term, this whole term into 0.15 XU, you will get 675 XU plus this whole term into 65, you will be getting 292 500. Then CU equals to 2475 XU. Add both these things, 1800 plus 675, then plus 292 500. Then you can equate CU equal to TU. Equating CU equal to TU. So CU is 2475 XU plus 292 500 and TU was 567137. So 2475 XU equals to, this will go this side and it will be subtracted, then 274,637. Therefore XU equals to 274,637 divided by 2475. So it comes out to be 110.96 mm. So your new XU is 110.96 mm. Okay, this is your new XU. When the neutral axis, when we had assumed neutral axis to lie in the flange, the depth of neutral axis was coming out to 105 mm and it was lying outside the flange. Then what we did, then we equated the total compressive force to total tensile force and then we got the new XU value, that is 110.96 mm. Okay, then you can just again find out the value of stress block parameter, that is YF, because XU is a known parameter now. So YF was 0.15 XU plus 0.65 DF. So YF is 0.15 XU, 110.96, just substitute 0.65, DF is 100. So YF becomes 81.644. If you look carefully in page number 97, besides this YF formula 0.15 XU plus 0.65 DF, it is mentioned clearly that it should not be greater than DF. Okay, this YF should not be greater than the depth of flange, that is DF. So the YF value is 81.644 mm, which is less than DF, which was 100 mm. So the satisfied, this criteria is satisfied. Hence XU equals to 110.96 mm is acceptable. Correct? First you have to find out YF, and then you have to see it should not be greater than DF, and then you can just mention that XU is so and so, that is in this particular problem 110.96 mm, which is acceptable. Now what you have to do, you have to find out XU max. Now from page number 70, if you remember, we have solved many problems by taking this XU max. This I will show again. Page number 70 you have to go of IS 456 2000, and you have to find out XU max by D value. For 415 grade it is 0.48. So from page number 70, IS 456, for FE 415, XU max by D value is 0.48. Then again the D value you know, therefore XU max equals to 0.48 into 400. So XU max comes out to be 192 mm. Now what you can write here, that XU max is greater than XU is greater than DF, because this XU max is 192 mm, which is greater than XU. XU was 110.96 new XU, and it is greater than DF, which is 100 mm. So if you look carefully, that XU max is greater than XU is greater than DF. Now again go back to page number 97 of IS 456 2000. What they mention here is in G2.3 clause, for XU max greater than XU greater than DF, which is in the present case, the moment of resistance may be calculated by the equations given in G2.2. okay, this is G2.2. okay, both are same codes. I am using these papers because I am not able to show you correctly. So what they mention here, for the moment of resistance may be calculated by the equations given in G2.2. so this is your G2.2 clause, and this is moment equation. Okay, again there is one clause, when DF by XU does not exceed 0.43, and G2.2.1, which is here besides, this is G2.2.1, the when DF by XU exceeds 0.43. in both cases substituting XU max by XU. So whatever the formula is given in G2.2, this moment equation, and G2.2, it is with respect to XU max, and what it says, when this clause is satisfied, XU max greater than XU is greater than DF, the moment of resistance may be calculated by the equations G2.2. this one, which is there on page number 96, G2.2, is taken when DF by XU, one more ratio you have to find out. I will show you in this problem. When DF by XU does not exceed 0.43, when the ratio DF by XU will not exceed 0.43, that time you have to go for G2.2, and when DF by XU exceeds 0.43, you have to go for G2.2.1, which is there on page number 97. Remember, when this clause is satisfied, you have to use XU value in place of XU max, because in both the formulas the XU max is given, you have to replace it by XU. Now what we shall do is, we shall find out this ratio DF by XU. DF by XU value. So DF by XU, DF was 100, XU is 110.96, and you will be getting 0.901. So DF by XU is greater than 0.43. Therefore use clause G2.2.1 on page number 97. So this we have shown, XU greater than DF, don't get confused. Okay, then what we did, we found out the value of df by xu, and in our present case df by xu is 0.901, which is clearly greater than 0.43. Then we have to use g 2.2.1 when df by xu exceeds 0.43, substituting this xu max by xu. So this moment equation we have to take g 2.2.1, and in place of xu max we have to replace it by xu. So write down the equation. mu equals to 0.36 xu by d. We have replaced xu max by xu. Other things remain same. 0.42 xu by d fck bw d square plus 0.45 fck bf minus bw yf d minus yf by 2. So the equations which this is borrowed from page number 97. The only thing is we have replaced xu max by xu. Okay, then just substitute in this. mu equals to 0.36 into 110.96 divided by 400, 1 minus 0.42, 110.96 divided by 400, fck is 20, bw is 250, d is 400 square plus 0.45, 20, bf is 750, bw is 250, yf is 81.644, then d is 400 minus 81.644 divided by 2. So this is the complete substitution you will be getting from this equation. Then just simplify it. The first term you will get mu, the first term, that is 0.36 xu by d, 1 minus 0.42 xu by d. Here this one, this first term when you simplify you will be getting 705 832 36.07 plus the second term, whatever is this 0.45, 20, the second term. Okay, you will be getting 131 961 278.8, and when you add these things you will be getting 202 544 514.9 in Newton millimeter, because all the things we have replaced in newtons and in millimeters. So the whatever you are getting the value will be in Newton millimeter, because we are calculating the moment. And if you want to convert it into kilonewton meter, then the mu becomes 202.54 kilonewton meter. So this is the moment value you will be getting for that particular T section. Okay, when all the parameters are given: breadth of flange, width of web, depth of flange, effective depth, AST, everything was given. You need to calculate the moment of resistance, and this is the procedure to find out the moment of resistance. Remember, first you have to assume the neutral axis to lie in the flange. You have to see whether it lies inside or outside. In this particular problem it was lying outside the flange. Then what we did, we found out the new value of xu by equating the total compressive force to the total tensile force. Then the new xu value we got. Then we calculated the yf, equivalent stress block parameter, and then again we have gone to page number 97. Then found out that xu max is greater than xu is greater than df. Then again we calculated the ratio df by xu, which was exceeding 0.43. That's why we have used the clause g 2.2.1 to find out the moment. Remember, we have replaced xu max by xu in that moment equation, and we have got the moment as 202.54 kilonewton meter for this particular T section. So it is little bit confusing, but it is also easy to solve this analysis problem. So if I have solved your doubts regarding analysis of T-beam, just like this video, share this video, and don't forget to subscribe all about structural analysis and design, and also press the bell icon for the latest notifications of my videos in civil and structural engineering. Thank you, friends.